Hello everyone, I think we are live again, so we are going to try this again and hopefully it works. The link will be posted in just a minute, so I will wait just a minute for that to be posted and then I will start. That way we can let a couple of people get in here, which will be nice, and we'll have some people watching. Okay, here we go. Waiting just a second to let a couple of people get into the stream. Okay, we've got a couple of people watching. Okay, here we go, people. We're gonna get going on this and we'll see what happens. So today I am going to be using three main programs. I'm going to be using OpenRocket here, and SolidWorks, and finally Cura, which is the 3D printing software that I use. So we're going to start out in OpenRocket. And OpenRocket is the tool I use to simulate my rockets and everything basically that I need to simulate for this program. It's a great tool. I really like it. So this currently is my Lyrid launch vehicle that I just launched a week or two ago. And yeah, this is Lyrid. So this is what you hopefully saw fly just a minute ago, or just a week or two ago. Sorry, I'm struggling a bit here. So yes, this is Lyrid, and really the big thing about Lyrid is that it was a major success. There were only a few minor problems with it, but those are rapidly being fixed. So one of the major problems that we originally encountered with Lyrid is this value over here where it says I'm not sure if I can't grab that, but that's fine. This is where it says stability 1.04 cal. So what we found is you want that to be between 1 and 2. So we're right on the nose at 1 there. One of the big things that we encountered right from the start was that it was at like negative 0.5, which is absolutely not what you want. And if we look over here, we can look at the first meteor we flew, and it was negative 0.134. So that was an error that I made that has now been fixed. But so and to fix that, I should explain how to fix that. So to fix that, part of what we've been doing is been trying to make the rockets as light as possible. So the fins, the body tube, the nose cone, everything was supposed to be as light as we could possibly make it. However, I learned that lighter is not always necessarily better, because when it's lighter, you have to deal with something called the pendulum effect, which is where the thrust coming in down here acts kind of like if you're trying to put your finger under a pencil and balance it, it's going to get really wobbly and eventually fall over. The pendulum effect is exactly that. You're applying a force at the bottom, and if it's super light, it's going to be really hard to account for the forces coming in from all sides of the vehicle. So what we had to do to prevent that is we had to put, you can see this little dashed line, that's representative of a mass of 72 grams up at the top of the rocket. And the benefit that brought to us was it allowed us to basically balance instead of balancing a pencil, it's more like balancing a bottle of hand sanitizer or something like that, where it's a lot more stable to balance. And so what we made Lyrid out of here is the tube is a high grade rocket tube. It's really good stuff. The fins are balsa wood, and then the nose cone and the engine block down here are both 3D printed PLA. And the total mass of this, as you can see right here, is 193 grams. So if you subtract 72 grams from that, it's 121 grams. And then you also have to subtract the motor. So it's somewhere around 80 grams. It's super light. It's amazing stuff. But light is not always better. So to start here, I'm going to save this as a copy, and if you could tell from the name of the save there, we're going to try and see what happens when we remove the weight here up top. And you can see the minute we do that, the stability drops to negative 1.39, which is not very good. So to fix that and account for that, we're going to try something else, and that is we're going to try and edit this body tube so that rather than 38.1 centimeters, it is instead of that, it is going to be a bit longer. Hold on, let me measure that tube real quick. Actually, I don't have to, because we can just double this, which is going to be 76.2 centimeters, or about 30 inches. And we can close that and save it, and you can see that brings our stability up to 0.357 cal. So that's with the longer tube. We usually actually, so that's the stock tube that we get, and in order to scale that, in order to make the Lyrid like we did, we cut one of those tubes in half. So that's if we use the stock tube, which is kind of what our next plan is, and that's going to make much longer of a rocket. And then rather than this nose cone, we're going to be putting in a different vehicle or stage, and that is this. This isn't quite finished yet, but this is the APHAC cargo carrier. And what that is, I will get a cross section here so you can see better what it is. You can see that this, have I passed over the fin yet? No. I want to cut that fin in half. There you go. That's good enough. You can see that this is a cargo pod, and so down this is all space where cargo can go. It's circular, so there's a lot of room in there. This wider section down here is a engine mount where we can put a class, B class, C class, anything up to really E or F class motor, which is a pretty decent motor. And then that will burn. It's pretty short, but that's okay, because the engine just sticks down in the next stage. We are going to be modeling this in OpenRocket probably today after I finish simulating it, or after I finish building it here, which is my next project. And we're going to simulate that in OpenRocket and see how it flies. I'm guessing that I'm probably going to have to deal with the pendulum effect a bit on that, but the plan is to put heavier things like batteries down in the trunk segment. It's somewhat difficult to see, but I think I can show you. This is made up of 3 parts actually. It's the trunk here, which has the fins, and then this space, and then the flame duct and engine mount. It's got the nose cone, which is the very top piece, which has I haven't actually put it in. It disappeared after my last save, but it has a hook for the parachute, and this will just sit on top and be an aerodynamic force. And then it's also got this aero shell, basically, that is a protection for the cargo. So you can see that in the diagram here, you can see that these match together, and it matches together up there. And you can, if you go look on the YouTube channel on some of our other videos, there's the APHAC boilerplate test, and you can see the first version of these that had a lot of problems, but that you can see that firing. So that's something I definitely recommend checking out because it's kind of cool. It was a partial failure, but it's something that we've already fixed a lot of the problems with, and that's something that we're going to continue fixing here. But this APHAC here is 100 times better than that one ever was, and I think one of these printed within the next few weeks will likely be the first thing that flies on top of a Lyrid stage. So part of the reason I was explaining all three different parts is in order to counter the pendulum effect, you want to have weight in the top or the upper part of your vehicle. There's the center of lift and the center of mass and the center of thrust that you have to account for, and if one of them's higher than the other, I can't remember exactly what it is right now, but I'll look in just a second here. If one of them's higher than the other, then it's going to be stable, and if it's not, then it's going to be unstable. So in order to counteract that, there's two ideas we have. One is either put the batteries down here in the trunk segment, because the engine is relatively long compared to this. It's going to go down to about here. So we think to counter that, we can put the batteries here, and that should stabilize at a good chunk. If that doesn't work in the simulations, we can also put them up here in the upper part and put the batteries there, which adds the weight in the nose cone, which should counteract the pendulum effect. However, that's something that remains to be seen from simulations. Two things I also wanted to point out real quick were these rounded bits here, and so the point of those is to add strength to the rocket. One of the problems we had with the first APHAC we built, that's what this is called, by the way, was that this engine and flame trench broke off. So by adding this is called a fillet. It adds structural strength, and instead of just having a sheer corner here that it can break, especially when 3D printed in the way we 3D print it, rather than having that, this will just it will absorb a lot of the force going into it, and it will add a strength at this right angle weak point. The same goes for over here. However, this is a more special part because this gap here is the exact size of the tube on at the top of Lyrid. It's the exact size of the inside and outside of this tube. So, you know, this will stick out a tiny bit over the end of that. And the point of that is that adds a mounting point, and as long as it doesn't have too much friction, which it shouldn't because we've built in quite a handsome tolerance there, then when this motor lights up from the parachute ejection charge on the lower stage, which spits out a ton of hot smoke and a good bit of fire as well, it will light this engine, and this will pull away from the vehicle, which allows it to act as a second stage and go higher than just the plain old the bottom of the rocket. And the advantage to that is that eventually we're going to have a lot of stages. The final design is 4, but I can definitely see it going higher than that. And part of what we're doing here is we're slowly just building up more powerful and larger rockets until the point where well, there's not really a stopping point to that, really. But so this acts as a second stage, and this will likely be the second stage that we fly. But the first stage eventually is going to be a lot bigger than this. So, with all of that said, and with all of that explained, maybe let's get some work done here. So to start, you can see we've expanded this, which is good. Now, part of the problem here is that it's still 0.357 cal, and that's a possible problem because it's not a high enough stability factor. So something that we're going to have to do is add a little bit of mass into the nose cone here. So that's really just something that I do by trial and error for the most part, which isn't always the best way to do it, but it's a good way to do it. So you can see this this blue and white checkerboard circle here. That's the center of gravity, and the red dot is the center of propulsion. So we're going to add a mass component to the nose cone, And really what we want to do is we want to bring the center of propulsion just above the center of gravity, and that should bring us above 1 cal. So we're going to grab a mass component, click, and you can see it adds it in the tip here. And last time we had a kind of a formula for doing this, but I think this time we're just going to kind of go, you know, maybe we're going to start with 50. That's going to be way too much, and you can see that brings our stability up to 3.4 cal, which is a bit much for what we want. It's a bit overstable. So we're going to make that maybe 20 now and see what that does. You can see even that is 1.83 cal, so it doesn't even need to be quite that much. So maybe we'll bring it down to 10 and maybe even 5 after that. Yeah, so this is a stability of 1.15 cal, and you can see the center of gravity isn't even exactly, or the center of propulsion isn't even exactly higher than the center of gravity, but you want you want it to be close to it, and more specifically, when the mass isn't here, when you delete the mass, take note of where that red dot is, and you can see they're pretty close. So this should function just fine with our current design. So we'll add a mass component. We can even probably bring it down to, you know, 5 grams, which is only a bolt or two. No, not quite 5 grams. Maybe we'll take that up to 8 grams. That should be plenty. Yeah, that's exactly 1 cal, which is kind of funny. So we'll make that 9 grams to be safe, and that should be plenty to keep us stable in flight, because you know, the first test stage was, oh, that's the other one. The first stage was, the first stage was 1.04, and that flew just fine, and this is 1.08. So this really should be just fine for our purposes. It should be plenty stable, and instead of perhaps instead of this weight, we will add our electronics, which I've got right here and I've just weighed, which are exactly 9 grams. That I don't know how I pulled that off, but that's quite impressive that I just said that exactly right. So, you know, there's probably some weight we're still going to add to that, and this isn't going to fly with just a nose cone for long, but it's a start, and we're going to work from that and continue onwards. So something else I need to mention, because I just mentioned it briefly in passing, but I should elaborate a bit on it, is that we are going to have electronics in this nose cone, and those electronics are going to be pressure, altitude, acceleration, temperature, and hopefully someday we're also going to even add cameras up there, so that we can get some really awesome views from the rocket. And that's something that's definitely going to be on the APHAC vehicle. So we're going to need to, you know, cut a hole in that or something to stick the camera lens through, but as we haven't really selected our camera yet, that's not a process that we're immediately working on. And if we decide to fly a camera on one of our first printed APHACs, we can always get a drill and just drill a hole in the aeroshell for the lens to go through. That's not something that needs to be designed in necessarily during the printing. Again, this whole section here is going to be 3D printed, and that doesn't always seem like it's going to be the best idea, because, like, how is this plastic going to stand up to the heat of the ejection charge? But from our testing with the first one we built, it absolutely is successful, and it's something that I was a bit worried about, but I think it's going to be okay, honestly, because it is, you know, we've tested and it's not a major problem. Hold on, I gotta get myself some water. This live streaming stuff is hard. I have a newfound respect for live streamers after doing this. Okay. So, continuing. Now that I've kind of gotten through show and tell and all that, I can move over to actually doing some more stuff. We've done a little bit here, but I'd kind of like to start getting some basic designs in for the the APHAC in OpenRocket, and I would also like to start going about getting some design or finishing up this design, because there's a lot of I mean, this looks really close to done, and it is, but there's a couple of minor problems that I want to fix. Like, I don't think that distance is quite big enough. Let me get my measure tool here and see how big it is. But I don't predict it's going to be a large distance. Yeah, like the direct diagonal there is 0.18 millimeters, and while my printer can do that, I'll take you to my slicing software here. My printer can go down to about 0.12 millimeters or more if I tell it to, but I'd like to have a bit more of a tolerance there, just because I don't want 0.6 millimeters of extra space there. It just feels sketchy, and frankly, I don't feel super confident in that working perfectly. So we're probably going to increase that a bit by either moving this distance out more or making this fillet less, probably a combination of both, because I think this fillet's a bit overdone here. But and then I'd also like to add some additional strength stuff. I'd like to add a fillet here. Surprisingly, so you may or may not know how things are 3D printed, but basically I will go over to the trunk here and you can see better. So basically this is the trunk, right? This is what we've got cut in half in the other drawing, and in order to imagine how this is going to print, we should look at it from this angle. And a 3D printer works by laying down small layers of material. So it'll start with this bottommost circle, it'll leave a gap there and a gap there, and it'll lay down a layer 0.12 millimeters thick, and then it'll move up a tiny bit, and it'll do another layer, and then it'll move up and do another layer, and it keeps going, and it'll build out these fins, and then it'll build up this, and it'll build up this tower, and once it gets up to here, it'll be done. And so it's a fairly simple process, but there's a lot of complexities added to it. For example, if we go back to the APHAC here, you can see that right here it's an empty gap, and then on top there's a bit of a lip here, and the same here, and the same on the fins. Actually, you can see that they if I go to this view, you can see that they slant up, they're not flat. And so you may ask, how do you go about doing that? Because when you're printing something, or you know, when you're building a building or something, you build from down up, and it's like an arch. If you don't have the keystone of an arch, it's not going to be structurally sound. So you usually have to have something to hold up that arch until you have the keystone, or until it's done, and then you can move that arch out of the way. Well, in 3D printing, that's called support material. And so for this design, you would have support material that would build up here and in here up to here, and support that while it's printing. However, it depends on when you need that support material. You don't always need it fully. And so something that I have learned, I have my additive manufacturing certificate, which is basically an industry certification in 3D printing and 3D manufacturing that that you can send to a job or a company or something, and as proof that you're capable of doing the job they need you to do. So I have learned through that process. It says you should always use support material over an overhang of 40 to 50 degrees. However, that's what they say by the book. Really, it depends on the situation. We printed this the first time without any support materials. We printed the fins. We printed everything here without support material, even though technically we should have used it. It just depends on the situation whether you really need to use it or not. And that's something that you learn from situational, and you learn from time and time again of 3D printing. And so this won't be printed with support material, but a lot of times you would need to do that, and it just depends on your printer. So that's how that's going to kind of be manufactured, but you don't need that specifically in this circumstance. And kind of the reason why we had to add this this fillet here on this fillet here was because when you're printing, you print it in layers across the screen here, as you print it horizontally, and so the connection between this tube and the rest of the vehicle was pretty weak because it printed along the layers, and the layers are weak to lateral force along the line of the layer. And so this was weak along that line, but by adding this fillet, it distributes that force, and instead of just having a shear force, it's a lot more distributed and stronger along that line. And so that's kind of why we needed to add that in, is because we saw that that was probably the reason why that failed, and we wanted to prevent that in the future. So without further ado, let's do some stuff here, because I've been talking a lot and it'd be nice to get some stuff done. So the first thing I'm going to do is I'm going to add a fillet here to make this stronger. And I'm really not picky with how much this needs to be. I'm going to make it 0.2 and I'm probably going to make it actually maybe 0.25 inches. Yeah, that seems good, because that'll go all the way to the edge here and really make that stronger. And if I were doing this a different way, I could probably add a small fillet there actually to make that stronger, and that will add more space for us to use. So I'm going to cancel that section view, and I'm going to make a small fillet here. I think it's not going to be big. It's just going to be something to continue the stress, or continue preventing the stresses there. And I'm going to actually cancel out of that and add a section view to see exactly what it's doing. Didn't mean to click that. I'm going to add a section view to see exactly what it's doing. So we can go in here, we can say we want a fillet, we want to select that there, and we'll see what that does. Yeah, so that's good, because you can see it keeps this interior space intact. You know, I think I should probably make that a little bit less, so we're going to go back and edit that, because that's not a very strong point right there. So instead of maybe 0.25, maybe we go 0.1 and see how that looks. Yeah, that looks a lot better. And these walls really don't need to be that thick. That's one thing we learned, is that the walls don't need to be thick on that. And of course, every ounce you save on that gives you an ounce more of payload capacity that you can use. So that looks a lot better, and now we can flip back over to here, and it'll say, do you want to update that? And we can say, yes, we want to update that. And now you can see that it's added in these specific fillets here that that we just added on the other part. Now, this is an assembly. This is what you call an assembly. The part we were working over here, this is called a part, and the APHAC is made up of 3 parts, and then you incorporate them all into this, which creates an assembly. And that's really a critical thing, because without that, we wouldn't be able to put together multi-part mechanisms. We'd have to make it all as one, and it wouldn't be able to move or anything like that. SolidWorks is also used really frequently for, you know, making a piston or something like that you want to be able to actuate the axle or the rod or whatever it's moving through, and check that it's going to work in the real world, and it's not just gonna run into other parts and things like that. Now, SolidWorks isn't perfect, and you have to have an understanding of the world, because in SolidWorks you can just glitch parts through other parts, or make two parts take up the same amount of space. You have to realize that that wouldn't necessarily work in the real world, but in SolidWorks, if you know that, then it's fairly easy to just manufacture things like this. Now, something you may be noticing is that there's not much, let me go to this view, there's not much tolerance built in here, and tolerances is a really important thing, because if you don't have a big enough tolerance, then it's not going to fit together, and that's problematic. But in this case, again, it's another situation of we've already 3D printed one of these as a test subject, and it worked in the 3D print, so we're going to do it the same way again, because we've tested this in the real world. Let me get another drink of water here. Wait, this is tough. Okay. So yeah, you can see that we've now got, we've now smoothed it out a lot, and more than just smoothing it out, we've made it more structurally sound. And the APHAC really, it comes apart into 3 different pieces, and there's a really good reason for that. The reason is this part up here holds in the parachute, and but when the exhaust comes up through here, the ejection charge, which if you don't really know what a parachute ejection charge is, go look at the first 2 videos, and even one of the more recent, a lot of the videos on our channel, a lot of the first, I think 4 or 5, were all static fires of model rocket engines. Which is what these fly on, and you can see really well there. You can see the fire coming out of the engine when it's burning, and then it waits a few seconds, and then it uses an ejection charge. All of the static fires on the channel were done with A8-3 model rocket engines, and really what a model rocket engine is or how you define, like if it's an A8-3 or a C6-5, you go on to you look at the engine, and an A8-3 is an A-class motor. That's the total impulse of the motor, which is kind of this is kind of an oversimplification, but it's basically burn time and power multiplied together through a complex equation. You can find it on Wikipedia. It's kind of a pain to just describe, but regardless, that's the total impulse of the motor. And then when it says -3 or -5 or -6, that number after the dash is the amount of time it takes between engine burnout and the parachute ejection charge firing. So all of the early static fires we did on the channel were done with A8-3 motors. So you can see in the slow motion, all of those are in slow motion, but it takes about it takes a good while, because it's 3 seconds in the real world, but like 24 seconds in the video before that that fully fires. Wait, this is difficult. So yeah, so something we're going to need to work on here is this whole section. There's a gap here, and that's because this nose cone was based off of the old design for this, which just had a static tube going all the way up to the top here, which isn't what we want anymore. Now we're kind of going to want to redesign both the base here and the nose cone. The aeroshell is going to remain mostly unchanged, but up here we're going to add a bit of an overhang with a fillet. Fillets are very helpful because they help you to print bigger and bigger overhangs without support material. So we're going to add a big segment here with a fillet in it, and then that's going to go up to here, and then the nose cone is going to be redesigned to probably insert inside of the interior of that just a little bit, and then have a hook on top for the parachute. So what it's going to do then is we'll have some recovery wadding, which is basically fancy paper. It's kind of like a stuffing paper, not wrapping paper, but like the paper you put in gift bags, basically to hide what's inside the gift bag. And what it does is it acts as a buffer, so that it burns away under the hot gases coming from the exhaust, but it pushes up and helps push your parachute out without your parachute getting completely scorched, which is bad if your parachute gets scorched. And so you can imagine the wadding will go down here, and there'll be a good amount of that, and then the parachute will kind of sit in this little cup here. You'd be surprised at how small parachutes can pack. Also, we're going to be doing testing to ensure that the packing doesn't cause problems, because the packing needs to be able to deploy quickly and easily so it doesn't fall out of the sky, kind of like Lyrid did in our most recent video. We've figured out why that was, though, we think. and I'll explain that in a minute. But then the parachute will sit up here packed, and then when the ejection charge fires, it'll push the wadding up, push the nose cone off, and push the parachute out, which will hopefully deploy and carry this whole thing down to a safe landing on the ground, allowing us to recover all of our electronics that I'd really rather not lose. So now moving on to why Lyrid failed, which is actually really interesting to me. So, you know, we have this weight up here that is 72 grams. That was done with nuts and bolts glued into the top here. There was a bolt glued in with a bunch of nuts screwed onto it, and then another bolt screwed into a nut that was kind of bridging the gap. But that added almost exactly 72 grams of weight to the nose cone. And that was great because it flew really amazingly. If you watch the video, you can see it flew straight as an arrow, which was better than I ever expected. But we think part of the problem is if you go to flight simulations here and go C6-3, we were flying this on C6-3 engines. You can see run simulations. It should pop up. Graph here, maybe. So altitude, vertical velocity, and vertical acceleration. We want to change that to G's of force. That's kind of what's used throughout the industry. So you can see that, and here's the exact problem, is it ascended, and then the recovery device deployment, that's the parachute ejection charge, fired before apogee. Well, that's great, but the ejection charge is strong, but not too strong. It's not incredibly powerful stuff. So the recovery device deployed before apogee when it was still going up and the nose cone was still being pressed into the rocket. Well, the nose cone weighed quite a bit, so it didn't have the force to push it off. And so the parachute kind of got pushed up against it and then stayed there. So when it flipped over and started falling nose first, the nose cone fell off due to weight, but the parachute didn't have gases hitting it and trying to push it out, because it had tried to deploy before apogee and not work. That's kind of what I'm thinking the problem with that flight was. However, if we go and do one small change, we have C6-3 motors, but we also have C6-5 motors. And so if we change this to C6-5 motors, which fired just a little bit after, it fires 2 more seconds after burnout, we can go back to flight simulations. We can see it now flies on C6-5 motors. We need to run the simulations. And if we can open this up now, units, G's, meters per second, we can see that the recovery device deployment will fire a little bit after apogee this time, which is a huge advantage, because by firing after apogee, we should be facing either sideways or downwards a little bit, and it should deploy easier because the nose cone will already be falling off due to the fact that it's falling out of the sky nose first, and the nose wants to work with gravity. Now, that's not as much of a margin as we had hoped for. I had hoped for it to be, a second or two after apogee, but it's something we can work with, and hopefully within the next week or so we will fly Lyrid again. Lyrid was completely undamaged after the first flight, so hopefully soon here we can fly Lyrid again, and maybe the nose cone will fall off and it'll deploy a little easier, or the same gases will fire, but it'll deploy easier because it has the advantage of working with gravity as that fires. So I personally think if we fly Lyrid again, the nose cone will deploy if we fly it on C6-5 engines, but I'm not entirely certain of that, and it's going to be a risk, but I'm happy to take that risk, especially since we're probably going to be retiring Lyrid soon for this longer version of the vehicle, which I don't have a name yet for, but that's fine. So that's kind of the plan for that. And hopefully, I'm thinking that Lyrid may fly with an APHAC on top of it, because it would mean that we wouldn't have to use those nuts and bolts, which would basically alleviate that problem. If we just had a ribbon or something to slow it down on descent, the terminal velocity was already super slow, which meant it was undamaged on landing. So it really doesn't need a ribbon, but a ribbon could help slow it down. And real quick, I'll show you what I mean by a ribbon. So there's the traditional parachute for model rockets, but there's also, you can see here, there's parachutes, but there's also a streamer, which is basically when you don't have the mass or you don't want to use a parachute, you can just use a streamer, which will slow you down quite a bit because a streamer or a ribbon is not super aerodynamic. And so it'll slow you down quite a bit by flapping around, and just slow you down enough so you don't fall into the ground and damage your rocket severely. And that's a really good thing because that allows us to still use Lyrid and have a higher chance of recovering it, but when the parachute ejection charge fires, rather than pushing this heavy nose cone out of the way, it'll light up a second engine. Now, one problem that I'm considering is the gases may not be enough to fill this entire tube. That's a probable problem that we will run into possibly on this, is the gases will just simply not be able to fill up this full tube and light up the next engine. That's something I'm working on and trying to figure out, and it's something I will thoroughly have tested before we fly, because a failure to light the next engine would very likely cause severe problems, and possibly even lead to a loss of the mission. So that's something that I'm really trying to work on and figure out rapidly, because I don't want a failure. That's not what I should be saying. I'm okay with failure. It's a failure that I could have, or that I had seen the possibility for, and that's not even the right way of saying it. I think that problem can be worked around. There are things that I don't know, and that's okay, because this is something I'm learning from. I'm not trying to build the perfect rocket on my first time here, and that's something I'm really trying to emphasize here, because the general idea is you need to build your rocket perfectly the first time so that it flies just right. And that's great, because you can go find a book at the library about how to build a rocket that will fly on the first time. You can go look on Reddit. You can watch a million YouTube videos about that. But you can't, there's something you learn by trying and failing. When I launched the first Meteor Test Stage, Ambition, I learned so much from that I wouldn't have learned by just flying, reading it in a book. There's something to be said for physical, hands-on learning, and that's exactly why I'm doing this. I'm trying to make it so that I'm able to fail, and when I do fail, I fail safely. I have fire extinguishers. I'm a good distance away. I'm wearing hard hats because I expect some rockets to fall out of the sky at high velocities. I'm expecting that. I'm okay with that because I'm doing it safely. And that's something that I'm really trying to hammer home here, is that I don't want to just read a book or watch a YouTube video about how to build a rocket and build that rocket. I want to do everything myself and learn from failure, learn from people who understand what I'm trying to do, so they're not trying to, force their opinion on me and tell me this is going to fail because XYZ reason. If there's a serious risk there, or if there's something that is actually going to be severely a problem, or if it's just going to blow up on the pad or something, I kind of want to know about that. But there's also a part of me that says, well, you're doing this safely. It's okay to fail and learn that, because you've got the time, you've got the resources. You can fail successfully without losing the whole rocket. And even if you do lose the whole rocket, you can fail successfully and be safe and learn more from it than you would have just learned by watching that in a YouTube video or something like that. Being able to dissect the rocket and look into what went wrong specifically and watch the video over and over again, there's something to be said for that. There's something to be said for being able to have been there and seen everything that went on rather than just watch it in a video. I know this kind of turned into a long rant, but that's that's something that's true, and that's something that I'm trying to emphasize here, is that I don't just want to read it in a book. I want to do it hands-on. I want to learn it all hands-on, because that's the best way I feel to do it. I've learned so much from this, and I've built a successful rocket. That's been seen. I haven't had a successful parachute deployment, but I think I know why in both cases, both on the APHAC test and on both of Lyrid's flights. I didn't succeed because of various reasons, but I learned why I didn't succeed, and I've now fixed that. So that's something that I'm really proud of, and I'm really trying to work on. Oh, I might have to call this soon here. Something else I want to point out. The apogee estimate here is 220 meters, and I actually don't have... What motors am I flying this on? C6-3. So I'm going to run a simulation on this and see, because I haven't actually run it on this longer tube. I just made that earlier. I've only run it on this tube, which, we saw how that went. This is now with the C6-5 engines. That's giving me hope, so I'm happy about that. But I want to run a simulation right now live on this and see what happens. So we're gonna do that real quick and see what happens. So I'm actually gonna start it on the C6-3 engines, just to see what happens. I don't exactly expect that to succeed, again because of the nose cone. But we're gonna run that simulation and see what happens. So we're gonna create a new simulation. Got all that. Simulate and plot. And then we want altitude in meters. X-axis is time. The y-axis, we actually have 3 different values, and you'll see how that works out. The altitude in meters, the vertical velocity in meters per second, and then the vertical acceleration in g-forces. A human can sustain about 10 g's for a short period of time. 10 g's is about where humans pass out. And much higher than that, you start risking more severe problems like possibly death, which is bad. So here we can see, again, the recovery device deployment is just before apogee. This is at like 5.3 seconds, and the recovery device deployment is at just under 5 seconds. And so that will probably fail in the same way Lyrid did. However, if I go here and I switch this motors and configuration, and I go to ejection charge delay as 5, and I say okay, then I can go back to flight simulations, run that same simulation now with 2 C6-5. This can support up to 4 engines, but right now we're just flying it on 2 because we found that when we went to 4 it caused some serious pendulum effect problems. So simulate and plot, altitude, vertical velocity, vertical acceleration. And you can see now that's even better because it deploys the apogee is a little bit later, which is interesting. That's just a result of the specific engines that we're flying on, and the recovery device deployment is a bit later. Now, if we fly this with an APHAC on top, which I'm going to be modeling in a bit, it will likely be, it will do the recovery device deployment just after apogee, and then fire up the next stage. Well, we don't really want it to reach apogee and then fire, because then it'll be like it'll be facing sideways. For the APHAC, we're probably going to want to fly on C6-3 engines, because the next engine will light up before we reach apogee and push that apogee even higher, and that really does, in a lot of ways, get exponentially more as the atmosphere thins, and as you get going faster, it's easier to go higher and faster. To a point. There's a point where you just spin out and lose control and then explode, which is bad. Sort of. Explosions can be kind of cool. So, yeah, I mean, the maximum velocity here is Mach 0.25. That's a quarter of the speed of sound. That is really fast. Honestly, that's insanely fast. One thing I wanted to look at real quick here. You can see vertical acceleration is in G's here. It's represented by the green bar. Something doesn't seem particularly right to me about that, because Oh, wait. Vertical acceleration in G's. Okay, here. So you can see if we follow this line across, that's about 21 G's. That's not something you would want to ride on because that's way faster. For clarity, the space shuttle, even the Saturn V. Let's look at the Saturn V. The Saturn V had about 2.5 G's at maximum acceleration, which is really kind of crushingly fast. It's not pleasant stuff. The space shuttle, I think, was around 3 G's. A launch abort system, which pulls you away from the rocket in case you start exploding, the launch escape system can go to about 15 G's. Well, at motor ignition, and sorry, I have the hiccups. At motor ignition, right after launch, we're going to be going 21, 22 G's of acceleration. So that's even faster than a launch escape system, which is absurdly high amounts of acceleration. If you were a human, there's basically no way, unless you were some superhuman, which some people have survived it and not passed out even. But a normal human would pass out instantly under that and possibly experience severe damage. Interestingly, you can see down here, we actually have negative G-forces for a little bit of time, right after motor burnout. Right after motor burnout, the G-forces drop to negative G-forces, which means we have basically a couple seconds of microgravity, which is awesome. And then that slowly burns off as you reach apogee. At recovery device deployment, you get a bit of shock from the device deploying and rapidly slowing you down. You can see the velocity is basically 0 at that point, which is really great. But then it slows down even more. And interestingly, you can see that instead it goes up maximum velocity of about 85 meters per second. I think the speed of sound is somewhere around 350 meters per second. But you can see at apogee, it stops being positive and goes into being negative, and then it's slowly accelerating to that until recovery device deployment, and then it slows down to a steady, maybe -2 meters per second or -3 meters per second. And that's with I don't actually remember how big my parachute is here. But real quick, the flight time of this is almost exactly 80 seconds, which is over a minute of flight, which is actually really great. Now, that's under ideal conditions. It probably wouldn't be quite that long, but that's still pretty awesome that something we are going to fly will fly for about 80 seconds. Now, the parachute on this, I want to actually look because I don't remember how large it is. So it's about 61 centimeters, which is, I think that's my 24-inch parachute. I can't remember. I think that's my 24-inch parachute. I have a couple of 12-inch, 18-inch, and 24-inch parachutes, and I can never really remember exactly which one I'm using. But I think on this I'm using the 24-inch parachute. So that's 2 feet across, which really slows it down. On the way down. It makes it so it floats down really slowly, which is great for prolonged flight time. On rockets that get higher and on the APHAC, which will be even slower or even lighter than this probably, we will have, a couple minutes of descent under parachute, which is great because that allows you to get a lot of consistent data about and a lot of data points about altitude, speed, velocity. Speed and velocity are the same thing, but altitude, temperature, pressure, forces, even camera footage. That'll be great for the YouTube videos. So yeah, that's kind of the advantage of having a larger parachute. Is the larger your parachute to a point, the the slower you go down. Now there's a point where it becomes kind of irrelevant, but again, that's not a point we're probably going to reach. So yeah, that's kind of the thought for this. This is probably going to be built within the next few weeks. I'd like to fly the first Lyrid again once more before then. Maybe I'll even try and get, you know, I don't know if I haven't even looked at this yet. This has just kind of come to me, but I might look into seeing if they have like a C6-7 motor, because if we go over here and we were to say, well, instead of C6-5, we want to fly it on a, come on, give me my little window. Instead of that, we want to fly it on a C6-7 motor. I'm pretty sure they probably make those. And you run, simulate and plot with the C6-7s, right? Yep. Plot it. You can see that you fall pretty rapidly for a good while, down to about 200 meters or so, 205, and then your parachute deploys. So that would really allow you some time for the nose cone to fall off. Now, you know, hopefully we won't need that, but worst case scenario, that gives you a good time for your nose cone to fall off. But again, with this bigger body tube, the nose cone doesn't need to weigh 72 grams. It only needs to weigh 9 grams, or whatever the nose cone weighs, and then an additional 9 grams on top of that, which really isn't that much. So you may not even need those C6-7s, but that could be something good for Lyrid, which we already have built, to see if you can get C6-7 motors and try and fly on those. So that's probably something we're going to look into in the next few days, but I think for now, that's probably all I've got in me for live streaming tonight. I'm kind of getting tired, and I'd like to go eat some food and get some sleep eventually, but thank you for coming and watching the live stream. I really appreciate you putting some time into watching this, and I hope you really enjoyed it. I hope we can do more of these soon and maybe have some more active development. I know this was a lot of overview, but I wanted to get into some deeper dive stuff into how failures have happened and what the plan is and all that sort of stuff. So yeah, thank you for watching. Please like and subscribe the video. You know, we're trying to get to, even though it's a little bit of a stretch goal, but we're trying to get to 1,000 subscribers soon so that it's easier for us to live stream launches. You know, I'm doing this on my computer here at my house, but in order to live stream from my mobile phone or anything, I have to have 1,000 subscribers, which is kind of ridiculous, but that's something we're slowly working towards. So please feel free to like and subscribe. It would really help us out, and hopefully we'll have more content coming to you soon. Please join the Discord, check out the website, etc. And thank you for watching. I hope you enjoyed.